Hello, and welcome to our conversation about force diagrams. So force diagrams are just drawings that show all the forces, and they're also called free body diagrams. So what we want to do is make sure that we account for every force that is acting on any object, whether it is at rest or in motion. The catch is, though, is that we're really focusing only on that object. We're not interested in any of the other objects except how they're affecting the object we're interested in. So if you have a book sitting on a table, we don't care about the table. We care about the force that the table puts on the book, okay? So let's talk a little bit about forces. Oh no, my picture is covering up the last force. That's terrible. All right, so we're going to deal with two forces. We're going to deal with field forces, and we're going to deal with contact forces. And like in the last video notes that you had where I told you that a force was a push or a pull, that's a contact force, okay? And so I found this little picture, which I think is really cute. Muscular force is kind of a fun thing, and it's like pushing, but that's not really what we're talking about when we talk about a push or a pull. Anything could do that, actually, but a lot of times we're doing it in class, so I thought that was fun. Friction was the other big contact force that we're going to deal with. So the push-pull and friction, right, both contact forces. The non-contact forces or field forces that we will sort of deal with, definitely with gravity, right? We're going to talk about the gravitational force a lot. There's also the electromagnetic forces, and this is where you're talking about things like electricity and magnetism. If we have time, we will talk a little bit about this. We're not going to go into depth because it's a Physics 1 class, but I will bring in electromagnetic examples as we are talking about these things, just so you can see that. And we'll talk a little bit about it when we talk about elastic forces and stuff. And then there are the nuclear forces, the strong and weak nuclear forces. And I am hoping that we will spend just one little day where we can talk a little bit about radioactivity, because that is one of my favorites. Yay! And there are forces, right, that are holding atoms together, and that's really important. Having said that, you will be talking about intermolecular forces in chemistry, which are electromagnetic forces, right? So you're going to see these again and again and again. Okay, so a little note on that. All right, getting back to our conversation about motion, what works against moving? Friction works against moving, right? And friction can come from the surface that something is sitting on, and it will apply whether an object is at rest or whether it's in motion. In order to get an object at rest to be in motion, you have to overcome that initial static friction. And then as you're moving along, in order to keep it going, and we saw this with the bowling ball, or if you had the marble adventure, you saw it with that, that you had to keep pushing on it to keep it going, but that's not really what Newton's first law says, right? But remember, that force is constantly working against you, so you have to apply a balancing force to keep it in constant velocity, just because there is a force acting on it. But I also don't want you to forget about things like drag, right? So there's friction of things traveling through the air, there's friction in things traveling through the water. So anytime you're in contact with any other matter, there's going to be a frictional force. So let's talk a little bit about these free body diagrams. We're going to do this in class. So if I'm talking about this and you're not feeling 100% sure, that's okay, because remember, these video notes are not to give you everything you need to know and then you just go off and do it. They're to give you something to think about before we get into class and go over it again, okay? So we can have a better conversation in class. So, oh, again, look, I've covered up my covered up my things there. I wonder if I can move this. Oh, I can! Look at that. That's so exciting. All right. Okay, so we use arrows to describe both the magnitude and the direction of the force. You can see that both of these arrows are the same length or the same size. You can kind of do it either way, but mostly we use length, the length of the arrow. And so we can see that it's a balanced force just by looking at the picture. It is also really good if you write the actual measurement next to it, so we can see that this is 100 newtons. Force is measured in newtons, and that is also important to know, okay? All right. There we go. All right, so when we're adding forces, we can only add forces in the same direction. So remember, the force diagram is the sum of all the forces, but we can only add them in the same direction. So the horizontal forces like right and left, so your forward push with friction, those would add together. And so here you can see F sub F is the force of friction. F sub A is your applied force, right? So I just said forward here, but really we're talking about the applied force. F sub G is the force of gravity, because gravity is working on everything on Earth. And then F sub N is the normal force. And normal force is going to be the force applied by the surface that the object is sitting on, right? So remember that book on the table? The table is applying a normal force on that book, right? And so it's the upward force in this case. If it's on an incline, the force is going to be that way, right, at an angle. And we'll talk about that later on. By the way, your secret word is normal. Normal is the secret word. Normal. Okay, so normal force is really important. So what we're really looking at is if the sum of the forces is 0, then the object is in equilibrium. And if it isn't, then it is not. All right, what about this? I just said that, let me move down a little bit. Okay. I just said that we have to apply the forces, or we have to add the forces in the same direction. What is going on here? Oh, no. Don't worry, though, because we don't have to worry. I'm going to put myself right over there. Boom. You don't even have to worry about that, because remember that we can break down geometry, right? We can actually make a cute little triangle because there is a forward force and there is an up force to give you this diagonal force. And so that's just a little preview. And the reason I'm showing you this now is not so you freak out. It's to show you that anytime you come across something that looks more complicated than you feel like you can handle, you want to just break it down into its smaller parts, right? Just stop for a minute, say, okay, what is actually happening here? And this is the other reason that we always draw pictures in physics. So you want to make sure that you are getting ready to do some great drawings. And don't worry, I'm a terrible artist. Most of my things are a circle with a word written in it. So it would be like a circle, cow, a circle, truck, right? So you don't have to be an artist, but we are going to be drawing everything, so get ready for that. Breaking things down, drawing so you can visualize what's actually happening to make it easier to see. Force diagrams are show all of the forces acting on the object, and they allow us to add those forces to figure out the net force so we can tell if the object is in equilibrium or not. All right. I will see you in class. Please make sure that you've written down your questions so that you can ask them when I see you. All right, that is it. Thanks for listening.